Okay, I think this is sodium. Okay, we have sodium on the top, and the idea is if we think about its number of valence electrons, it just has this one little guy here. The 3s is its highest number, and it only has one electron there. So it's cool getting rid of it. Chlorine is completely full, minus, it has one little spot at the end of its valence electrons here. So it has 7 valence electrons. So it's like, give me that electron. When these things do that, they become oppositely charged and then therefore attract each other. Okay. So we have kind of that same breakdown here. We have a sodium and chlorine. You start with two separate atoms, a metal and non-metal with no charges. Sodium chooses to give one electron to chlorine, passes it over. The atoms now have a charge and become ions. This one lost an electron is now a positive one charge. This one gained an electron is now a negative one charge. They have opposite charges and now they stick together. Right. Covalent bonds, atoms held together by shared electron pairs. Each pair of shared electrons creates a bond. So, if each atom contributes one electron to make a total of two, that is a single bond. So you can kind of see that in this example with hydrogens. Each hydrogen is going to give one of its electrons up, put it in the middle, and that's 2 electrons total being shared between the atoms. And we draw that with a straight line like this. Now with oxygen, oxygen makes a double bond with itself. Okay, it has 4 electrons, which means 2 from this oxygen, 2 from this oxygen. Put 4 in the middle to share them, and then they make a double bond. We draw that with 2 arrows. So that's 4 electrons total being shared. And over here we have nitrogen, and nitrogen would do a triple bond. So that has to share 6 electrons total, and then it has 2 more each by itself. Talking more about energy of bonds, especially with double and triple. In general, shorter bonds have more energy. Double bonds are shorter than single bonds and have more energy. Triple bonds are shorter than double bonds and have more energy. So as you add additional bonds, a double bond or triple bond, kind of think about it, it's like much shorter. It holds them a lot closer together. So the single bond is actually the longest, the distance is the longest, and then as you add more bonds, it kind of gets shorter and shorter to each other. And you can kind of think about it. If you have a really long, thin object, it's really easy to snap. Okay? And as that object gets shorter and shorter, though, it's harder to get leverage and snap it. And bonds work the same way. The longer something is, the easier for it is to break. So a very long stick is really easy to snap in half, but a shorter piece is harder to snap. And then the triple bond is the shortest, and that is the hardest to snap. And that means you need more and more energy to actually break it. So double bonds are shorter and harder to break than single bonds. Triple bonds are even shorter and even harder to break than double bonds. We can compare the approximate bond energy by comparing the size of atoms. The number of bonds is also called the bond order sometimes. So you might see that in a question. A triple bond has a bond order of 3. Double bond is bond order of 2. It's just another way to say single, double, or triple. All right. We have some of these graphs again. These little dip graphs, the intramolecular force plot here. And we have 3 different ones here. This one says higher bond order, meaning triple bond being the highest, single being the lowest, tend to have more energy. These are the energy curves for H2, N2, and O2. Which one is which? So you need a little bit of info, which we're going to learn later this chapter. H2 is a single bond, which we just kind of showed you that picture of. N2 is a triple bond. O2 is a double bond. So we can kind of use this graph to figure out which one is which, based on their energies. We learned triple bonds are the hardest to break. They have the highest energy. And so that would make this red curve here N2. Now, we said it should be the shortest. So you'd expect it to be all the way to the left. But hydrogen is super extra small. And that's why this one over here, we're to learn is hydrogen, because it's the lowest energy. And it also happens to be small. So that's the only reason that kind of goes against that pattern I showed you. Hydrogen here is much smaller than nitrogen individually. So even though this bond might be shorter, the atoms are so much bigger that the bond length has to be larger. This purple one here is in the middle of energy, so it'd be the double bond, which is oxygen. And that one does follow the trend that it's further to the right than nitrogen. The bond length is a little bit longer for oxygen. That's a fairer comparison because oxygen and nitrogen are basically the same size. So when you compare their bond lengths, the triple bond one you'd expect to be a little bit shorter, which it is in this case. So the shorter bonds are generally harder to break. The higher bond order are also harder to break and would have more energy. All right, our next topic we have to talk about is polarity. Now, this one gets pretty complicated. You've talked about polarity before, but we really have to think about it in a chemistry context. Covalent bonds can be classified as polar or nonpolar. Now, polar bonds don't share electrons evenly between the atoms, meaning one atom is being a bully and stealing more of the electron density to itself. This means that it's an uneven distribution of charge across that compound, meaning the compound will be partially charged itself. If more electron is on one side of the atom, that atom side on average is slightly negatively charged. And the other side that's lacking as much electron as it's expecting is partially positively charged, meaning it's a polar compound. It has like two poles, a north pole that's positive or negative, doesn't really matter, and the other pole that is the opposite charge. This means because it's polar, it interacts with other charged particles. Anything with a charge will attract other things with a charge because of Coulomb's law. The opposite is nonpolar bonds. These are ones that share their electrons completely equally. It means that there's a completely equal distribution of charge. No compound or no part of the compound is positive, no part is negative. It's all pretty much just plain and nothing. The compound will not interact with other charged particles because of this. So a polar particle you can think would be attracted to a magnet, but a nonpolar one wouldn't. It all has to do with how well they share electrons. That also comes down to the electronegativity. A nonpolar covalent bond between nonmetal atoms consists of an equal or almost equal sharing of electrons. It has a zero, or very close to zero, difference in electronegativity. So I kind of said that before, but here's some examples. If you have two nitrogen atoms, for example, we'll learn in a second they both have an electronegativity of 3. And that makes sense that they'd be the same because they're both the same atom. So that difference is 0. That would be a perfectly pure covalent bond, also called a nonpolar covalent bond. So anytime you have the same atom bonded to itself, it's always nonpolar. Our other example here is chlorine and bromine. Chlorine's electronegativity is 3, bromine's is 2.8. So when we subtract those, we get a difference of 0.2, which is less than 0.4. So even though there's a very slight difference, it is not noticeable at all. So we still consider this nonpolar covalent. This molecule would not be polar. It would not attract things with a magnet, it would not attract other polar compounds, etc. The opposite is a polar covalent bond. This is between nonmetal atoms consisting of an unequal sharing of electron. The atoms have an electronegativity difference between the 0.5 and 1.7 range. So our three examples here, we have oxygen, 3.5 electronegativity, and chlorine, which is 3. That's a 0.5 difference, which is just at the bottom side of this range, but that's okay. We're still going to consider it polar covalent. So this is polar, meaning this bond would attract things with a charge. CCl bond is a 0.5 difference, so same thing, it's still polar covalent. And N and H, the difference between those is 0.9, which is a polar covalent bond as well. I would expect the most polar of these to be the NH bond, which it is the most polar. Here's another sort of image to sort of visualize this. On the left, this is a picture of a completely non-polar bond, which makes sense because it's two hydrogens. Of course, they're going to share electrons the same because they're both the same thing. We see this electron cloud, the area where the electron can kind of go is the same. Okay? Then I have this version over here as a non-polar, right? Is a polar situation. Chlorine is much more electronegative than hydrogen, so chlorine takes a little bit more of the electron space to itself. You can see in this case, these electrons are right in the middle. In this case, they're a little bit more in the green space, in the chlorine space. So it's stealing the electrons a little bit more to itself. That would mean that chlorine is a little bit negative and hydrogen's a little bit positive because it's lacking an electron. These little symbols, these little deltas with a positive or delta with a negative, are used to represent that. So let's do an example here. We want to complete the following table for each of the bonds indicated. So the first one, I have Si and I have S. Okay? I'm going to find the difference. I'm going to write the type of bond based on that information before. At the bottom here, I have the electronegativities for you. There's a couple that I have written down for you on your notes that you'll kind of need, But these are examples of ones you wouldn't need to know. This would have to be given to you to answer this sort of question. All right, so the first one was an Si-S bond. And according to what we have there, Si is 1.8, S is 2.5. I'm not really worried about positive or negative here. I'm just worried about the difference. So I can take the absolute value if I want or subtract them in whatever order. But the difference between those two is 0.7, which is greater than 0.4. So this is polar covalent. Okay. The next one is a CS bonded to a Cl. CS's electronegativity is 0.7. Chlorine's is 3. So if I subtract these, that's a 2.3 difference, which is greater than that 1.8 boundary, meaning this one's not covalent at all, it is ionic. The last one, we're combining Si and P. Now silicone is 1.8 electronegativity, phosphorus is 2.1. That difference is 0.3. Okay, that falls actually less than 0.4. So this, even though there's a slight number here, would be a non-polar covalent bond. And that's kind of our main idea of what we're doing here. The difference in this number, this electronegativity, which is not something you have to memorize, can be used to figure out what sort of bond you would make. Here are a couple I would highly recommend you know. And you don't need to know the exact number. You need to know kind of, these are very common atoms in covalent bonds, probably the 6 most common ones we'll use. And you need to kind of know which combinations make a polar bond and which combinations don't. So I have the values over here for you. The main takeaways I want you to know. Number one most important thing is what I'm having you write down. It's that carbon and hydrogen always form non-polar bonds together. Meaning if you have a carbon and hydrogen bonded to each other, that is not polar. That difference is 0.4, which we're going to consider the lower end. So we're going to we're going to kind of round it down a little bit, I guess, right? And call it non-polar. But if carbon is bonded to any of these other things, which happens very commonly, to nitrogen, chlorine, oxygen, or fluorine, or if hydrogen is bonded to any of these other things, that is always polar. No, it's another typo. So change in your notes real quick, where it says we'll make a non-polar bond. That's supposed to say make a polar bond on the second one there. So just killing it today. So you're welcome. So carbon and hydrogen bonded to any of these four will always be polar. It's always going to be a greater than 0.4 difference. Okay. Bonds become more polar as that difference in electronegativity increases. A polar covalent bond that has a separation of charges is called a dipole. Dipole and polar, you can kind of see that they're similar words. They both contain that pole. Pole meaning like you have a positive and negative end. Dipole just means you have two ends of a polar molecule, right? Positive and negative ends. The positive and negative ends are represented by the Greek letter delta with a positive or negative charge. You also can draw these little fancy arrows called dipole moments. And these kind of show you where the charge goes. So they're always these arrows with a little tail. And the little tail is going to be the positive end, and the arrows are always going to point towards the negative end, because you're pointing towards where the electrons are going. Let's do a couple of examples of those. I'm going to draw dipole moments for each of the following bonds, if they have one. So we're going to start with the CO bond. So this is kind of where we need that electronegativity information from before. Carbon's like 2.5, oxygen's at 3.5. That's a 1 difference. So this will be polar. And the electrons are going to go towards the end that's more electronegative, which in this case is the oxygen. So when I draw my dipole moment, I'm going to draw it pointing towards the negative one, towards the electronegative one, towards the oxygen. Put a little tail by the positive one. This means this end is partially negative. This end is partially positive. So you could either draw these little symbols to represent that, or this arrow. The next one is the CH bond. We learned the CH bond is always nonpolar. The difference is only 0.4. So we're going to say it's nonpolar. So you could not draw an arrow. Even though this one is slightly more electronegative, you would not draw a left arrow here, okay, because it's nonpolar. Next, we have the HF bond. We have hydrofluoric acid. Hydrogen's around a 2.1. Fluorine is the most electronegative element at a 4. That's a pretty big difference here. This is a difference above the threshold for electronegativity to make it ionic bond. But this one is actually not going to be an ionic bond. That table is a good guide for estimating, and I will say the number one thing that messes with it is hydrogen. Hydrogen is kind of a weird exception. Hydrogen makes a perfectly polar or nonpolar bond with carbon, even though the difference is pretty big. And this difference would lead you to think that this is an ionic bond, but it's actually not. So when you see hydrogen bonded to stuff, just know this is kind of be an exception. Hydrogen and fluorine will make a covalent bond, but it will be very, very polar. So this is actually one of the most polar bonds that exist, but it is not quite an ionic bond, even though it is above the number I gave you. So we will draw the arrow this way, towards the bigger number here. The last one is the iodine bond here. I don't know what iodine's number is, but it doesn't matter because it's going to be the same. This is definitely nonpolar. Okay, a bunch of fun exceptions with hydrogen, so those would be fun to deal with. All right, we're to our last topic for today, which is Lewis structures. Here's a whole list of drawing Lewis structures. If you like lists and instructions for how to do things, go for it. I'm much better at like looking at examples and stuff like that, so that's what I have for us to do on the next slide. And I think it'd be more helpful to run through the example first, or at least do a couple of them with me, and then read through this. So I'll let you kind of do that in your own time because that doesn't mean anything until you do it. So here I have 4 of the most common Lewis structures, and we're going to draw these together to kind of show you how. All right. So it says draw the following Lewis structure. We're going to start with CH4. Okay, so a Lewis structure is a picture. Hopefully you remember it from Honors Chem. This is like one of the bigger things about this topic for sure. The AP test is covered with Lewis structures, having to interpret them or having to draw them. It's basically a 2D sketch of what this molecule looks like. Okay, we're going to do a couple of the steps. That doesn't make sense. We're going to draw it. Okay, the first thing you're going to do is you kind of have to draw what the molecule is going to look like. There's going to be a molecule at the center. So the center of our picture here is almost always going to be your first element. And in this case, it will be. There's kind of an unfortunate thing where you just have to get a feel for how these sort of work. There's a couple of rules, but they're more complicated than just actually drawing them. Okay, so your first element will go in the middle, and your other elements, in this case hydrogens, which I have 4, will go around it. And you're just going to kind of like spread them out as much as you can, preferring them to be symmetric. Atoms really like to be symmetric. So I'm going to draw each of the 4 around the center. I'm then going to draw a line to each one. Okay, so each line represents 2 electrons. Okay. And those 2 electrons are actually being shared by both atoms. So both X and Y here get 2 electrons from this bond. They're being shared. Now, every atom wants to have generally 8 electrons total, meaning some combination needs to add up to have 8 electrons, and that's called the octet rule. Now, there's a few exceptions to that. Number 1 most important exception being hydrogen, which we have 4 of in this picture. Hydrogen, because it only has an s orbital, can only hold a max of 2 electrons. So most things will want 8, right? Oxygen wants 8, nitrogen wants 8, fluorine wants 8, chlorine wants 8, right, etc. Most atoms will go for 8. Pretty much any atom by default, that's sort of the amount you're going to give it. What else? We have carbon, we have phosphorus, we have all the different nonmetals here that make these sort of bonds. Okay, want 8 electrons, but hydrogen specifically wants to have 2. So over here in our picture, we drew C in the middle, H's all around. We drew a line to each one. That line is a covalent single bond. So if we think about each hydrogen, this hydrogen has 2 electrons right now, which is perfect because this bond, it only wants 2. This hydrogen has 2 electrons from this bond. So does this one, so does this one. So with only one line, all those hydrogens are satisfied. Now think about the carbon. The carbon is currently attached to 4 bonds, which each of them give 2 electrons, which is perfect because most things want 8 electrons, including carbon. Okay, so this picture is actually already perfect, right? Your carbon has 8 electrons, so its octet is full. Your hydrogens have 2, so their valence shell is also full. So that is your drawing. There's only one more thing you kind of have to do at the end. I just kind of made all these lines out of thin air. I have to make sure I actually had these electrons available when these things all come together. So another aspect of drawing a Lewis structure is when you draw it, you're going to write the number of valence electrons that everything has and add it all up together. Their valence electrons are what they're going to be able to share to make their sort of structure. So carbon has 4 valence electrons. If you're not sure, you can just go back. That's not what I want. You can just go back to your periodic table. And remember that the first column is 1, the second column is 2, 3, 4, 5, 6, 7, 8. Carbon is 4. Okay. Carbon has 4 valence electrons. Hydrogen's in the first row, it only has 1. But there are 4 there, so I have to times it by 4. Each hydrogen provides 1 valence electron. So 1 times 4 is 4, plus 4 equals 8. CH4 allows me to use 8 valence electrons total. That's how many electrons they all have to share. And fortunately, this is a simple one, so that's how many electrons are in my drawing. Each of these lines was 2, remember? So I've used 8 electrons in my drawing, and everything is happy, so I am done. Okay, there's a lot going on there. It's kind of a mess. Let's kind of run through another one to get that procedure down. Okay, our next one is NH3. So I want to kind of remember all these rules. I'm going to start by thinking about how many electrons I have to use in my picture. I'm going to find how many valence electrons nitrogen has, which is 5. And again, hydrogen has 1, but there are 3 of them. 1 times 3 is 3, plus 5 is 8. Again, this drawing should have 8 electrons total. I'm going to pick my atom to go in the middle of my drawing. I'm going to choose the first atom unless I have a reason not to, which as of now we don't have any reason not to. And this time I have 3 hydrogens, so I'm going to spread those 3 around the center. If yours looks slightly different, that's fine. There's all sorts of different ways. But the idea is the hydrogens would rather not be next to each other. They're going to try to spread out as much as possible. Draw a line to each one. This is called our skeleton structure. And on the last one, it happened to be our final answer, but this is kind of rare. It's only for very simple ones. This is our skeleton. All of our things drawn in the right spot with a single bond to each of them. But we don't know if everything's happy yet. So let's start with the hydrogens. Hydrogens want 2 electrons. They're already happy. All 3 of these hydrogens have 2 electrons. But nitrogen, like most other things, wants 8. It currently has 6, 2 from each of these bonds. So I need to give it 2 more electrons. And this is where we go to the next step. You're going to add valence electrons in pairs as these little dots until everything is happy. So it had 6, it needed 2 more, so I drew 2 little dots called a lone pair on the nitrogen. These are 2 electrons that belong only to the nitrogen and nothing else. So these are not being shared. These are being shared, these are not. Okay, so this is what our drawing looks like. I have nitrogen in the middle. It now has a total of 8 electrons, 6 from the bonds, 2 by itself. So now it is happy as well. Last thing I need to do is make sure I used 8 electrons in my drawing. 1, 2, 3, 4, 5, 6, 7, 8. We're good. Our next Lewis structure is CO2, carbon dioxide. I like to start by thinking about how many electrons I can use in my drawing. Carbon has 4 again. Oxygen has 6. It's in the 6th column there, if we're not counting in the middle. times 2, because there's 2 oxygens. That's 12 plus 4 equals 16. I have 16 electrons to use in my drawing total. I'm going to start drawing the skeleton structure. C goes in the middle, because it's the first atom. O's you put symmetrically around. So I'm going to choose to put one on the left, one on the right. Draw a line from the center to each other atom. Now I need to make everything happy. So I'm going to start with my oxygen on the left here. It has 2 electrons, but it wants to get up to 8. So I need to add 6 extra dots. And I'm always going to add them in pairs, called lone pairs. And I'll add 2 to each side to bring this up to a total of 8 electrons. I'm going to do the same thing to this oxygen. I'm going to give it 6 more electrons. Now it has 8. Don't forget about the carbon in the middle. It has 2 electrons from here, 2 electrons from here. It needs 4 more. So I'll add 2 up here and 2 down here. And with that, everything is happy. So that's your steps, right? In the middle, carbon atom. Draw a line to every other atom. Add lone pairs until everything is happy. Then we verify to make sure we only use 16 electrons in our drawing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's a problem. My drawing works, but I use too many electrons. I don't have 4 electrons here that I want for my drawing to work. So I need to find a way to conserve electrons. If we think about a lone pair takes 2 electrons, but it's being inefficient. It's only giving those 2 electrons to one atom. A bonding pair is 2 electrons, but it's sharing those. These 2 electrons are more efficient because they count as 2 for the carbon and 2 for the oxygen. So if you have too many electrons in your drawing and you need to reduce it, you can get rid of 2 lone pairs on adjacent atoms, like this, and replace it with 1 extra bond. That extra bond is a double bond. That saves 2 electrons total. If I recount, I've only used 18 electrons now. Which means if I do this one more time, I can get down to 16. So I'm just going to choose to do it on the other side because it's more symmetric. Get rid of 2 here and 2 here. And replace it with an extra bond. I'm down to 16 electrons, which is good. I just need to make sure everything's still happy. Which if I check, everything is, because this has 4, 5, 6, 7, 8. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. Oxygen also has 8 over here. The last one we have here is N2. Nitrogen has 5 valence electrons. There's 2 of them in this drawing. I have 10 electrons to work with. Now here's a situation I don't really have a center atom. Okay? It doesn't really matter which one you pick then. Because you only have 2 of them, just draw them next to each other and put a line between them. There's technically not one in the center, but you wouldn't really be able to tell the difference anyways. It's relatively simple. Draw a line, add lone pairs until everything is happy. Nitrogen, like everything else besides hydrogen, wants 8 electrons. So I'm just going to start by drawing up to 8. So this is 2, 4, 6, 8, and 2, 4, 6, 8 over here as well. Nitrogen's super happy. I just need to make sure I didn't use too many electrons, which it looks like I did. This drawing uses 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons. So I need to do what I did up here and reduce that number. I can get it down to 12 if I cut out these 2 and these 2. Doesn't matter which pair you pick, but just get rid of 1 on each adjacent atom and replace them with 1 bond extra. That gets me to 12, but of course I need to go down to 10. So I need to add another bond, getting rid of a lone pair. Now if I count, I've only used 10 electrons, but each nitrogen is happy. So earlier we said nitrogen makes a triple bond. This is why. That's just what works out in its Lewis structure. That's the only way to arrange that number of electrons to make both atoms happy. Lewis structures either make your brain really happy because it's like a puzzle, or you hate them. But that's okay. It's okay if you hate them because there are a bunch of weird sort of rules, and we're going to talk a little bit more about those kind of in these next couple slides. Um, yeah, it's okay. Speaking of which, here's a whole bunch of exceptions. The octet rule, like we said, says all atoms will bond to have a completely full or completely empty valence shell. Most of the time, they'll bond to have 0 or 8 electrons in their valence shell, but there are some exceptions. That first one we've already mentioned, hydrogen. Hydrogen can only have 2 electrons. Because it has no p orbital, there's no 1p orbital, it can only hold up to 2. Now, beryllium and boron are super fun. They have a bunch of flexibility. Beryllium and boron are atom number 4 and 5, so they're kind of tiny with their amount of protons, neutrons, and electrons. They can do some weird things sometimes. They can have either 4, 6, or 8. It can have any number of those depending on what's best for your drawing. So sometimes your drawing works out and boron or beryllium will have 8 electrons, and that's super fine. But it also can have 4 and it also can have 6. So we'll get some examples like that in a bit, but just keep that sort of in the back of your head. If you have one of these B ones, they can have a lesser amount sometimes if it works for your drawing. Now these other ones are larger atoms. Sulfur, xenon, phosphorus, chlorine can have 8 or up to 12. Okay, so they can have 8, 10, or 12. And I should have listed that out. So if you want to, these are 4 examples that can have 8, 10, or 12 electrons. You'll notice it's always an even number, and that's sort of a Lewis structure thing. You only deal with electron pairs. You don't have single electrons. So you'll never have something with 11, for example. Let's do these 2 examples of things that are exceptions to the octet rule. So you're going to treat them pretty much exactly the same. BF3. Okay. Boron's kind of a weird one. It has 3 valence electrons. Fluorine has 7. And there's 3 fluorines though, so I times that by 3. So I do 7 times 3 is 21 plus 3. I have 24 valence electrons for my drawing. Boron in the middle. My 3 Fs, I'm just going to kind of put around somewhere. Pen. Okay. And draw a line to each one. I'm going to add electrons till everything is happy. Fluorine wants 8 electrons. It has 2. I got to add 6 more. And I'm going to have to do that 3 times for all the fluorines. Boron's in the middle. Boron, when I see it, I'm like, okay, this can have 4, 6, or 8 electrons. Okay. It's going to do whatever works out the best for the rest of the atom. So currently it has 6, which is acceptable. So I'm going to hold off adding any electrons to it. But if I need to add more to get up to 24, I can. Or if I need to find a way to try to take away electrons, I can try that as well. So I'm just going to count up how many electrons I used in my drawing. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 20, 22, 23, 24. Okay. There's no reason to add any more electrons to boron. That would just complicate things because I already have the perfect amount. If I had, for some reason, maybe this number is 26. Maybe I had a negative charge here and had some extra electrons. Instead of 24, I had 26. I could put those electrons on boron and it would be perfectly content doing that. But in this situation, I don't need to. Because I have 24, I'm just going to stop there. So that would be our final answer. All right. We also have PCl5. Okay. Phosphorus has, let me double check. It has 5 valence electrons. Chlorine has 7, and there are 5 of them. 3 times 5, we got 35. Plus 5 is 40. Let's put phosphorus in the middle because it's the first one. Chlorines, there are 5. So I'm just going to try to space all those around as nicely as I can. Okay, my chlorines, I want to make them happy. They have 2 electrons, they need 8. So each of these chlorines is going to get 6 additional electrons to make them satisfied. Chlorines are all happy. Let's think about phosphorus. Phosphorus has 10 right now, which is more than 8. But phosphorus was on that list. Phosphorus is okay with 8, 10, or 12. So I can even add 2 more electrons to it if I need to. But let's check to see if I need to or not. So this is 8 electrons plus 8 plus 8 plus 8 plus 8, or 8 times 5. My drawing has 40. Because of that, I'm good. Phosphorus can stay just like it is. We're good. So there's some atoms with some flexibility with their number of electrons, and that takes a little bit of practice to kind of get used to, and that's why I like to draw with this method, where I fill everything with electrons first, and then I count to make sure I use the right number of electrons before dealing with like these weird ones. Okay. Last thing today, polar or non-polar molecules. We learned that a bond can be polar, but we need to apply this idea to an entire molecule now that we can draw them. Once you draw a Lewis structure, draw the dipole moment for each bond. Any dipoles going in opposite directions cancel each other out. If any dipole moments remain, then the molecule is polar. This is another thing easier to see, so let's do our example. I have 2 molecules here, and we want to figure out if they are polar. You cannot do that without drawing their Lewis structures. So, now that we know how to do that, let's give that a shot. Starting with CCl4. Carbon has 4 valence electrons. Chlorine has 7. I have 4 chlorines, so I'm going to times that by 4. 28 plus 4, 32 electrons in my drawing. Carbon in the middle. Take my 4 chlorines, space them all around however I want. Notice all of mine are looking a little bit different. That's fine. I'm just mainly trying to keep them separate from each other. All right, let's make everything happy. Let's make everything satisfied. Also notice I'm doing this entire thing in pencil because Lewis structures in pens can be dangerous sometimes. All right, so let me check my electrons, make sure my drawing's good. I don't need to make any extra bonds. I have 32. 8 times 4. So my drawing's good. Now we're going to think, is this thing polar or not? I have 4 CCl bonds here. Chlorine has an electronegativity of 3. Carbon is 2.5. This bond is a little bit polar. So I'm going to draw my arrow going towards the chlorine. And I'm actually just going to physically draw that on my Lewis structure. Towards every chlorine. So towards that one, towards this one, down towards this one, up towards this one. So my molecule must be polar, right? Because I have all of these dipole moments. Except it's not. All of these cancel each other out. The one going up this way is completely and oppositely canceled by the one going down this way. These 2 dipoles are completely opposite of each other. So that, essentially, those 2 cancel each other out. These 2 are the same. One's going completely this way, one's going completely this way. They cancel each other out. Even though this thing's made of 4 polar bonds, the entire molecule is non-polar. The symmetry of the shape cancels out the polarity. That can be tricky. That's one of the harder things to grasp with this chapter. You have to know the Lewis structure, and you have to be able to apply this idea. So we're going to do this a lot together. Here's my next compound. This one looks a little bit more complicated, and that's okay. The Lewis structures do get more complicated as we go. Let's talk about how to draw this, though. It's essentially the same idea, except instead of CH4, I have different things to put around my center C. C goes in the middle still. 3 of the things attached to it will be an H, and it doesn't really matter which order I choose. 1 of the things attached will be a Cl, and that's how you would kind of read that. C with 3 H's and 1 Cl. I have 4 plus 3 plus 7 equals 14 electrons to use in my picture. My hydrogens, these 3 are already good, so I don't have to do anything to them, but my chlorine needs 6 more to get it up to 8. My drawing is used 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. My drawing's good. We already learned the CCl bond is polar. So I'm going to draw a dipole this way. The CH bond is not polar. Always. This is non-polar. So that means there's no arrows going anywhere else. If I'm thinking about my entire molecule now, I only have one dipole, so there's nothing to cancel it out on this side. So this molecule is polar. You would say this side of the molecule is partially negative because of this dipole moment. Cl is dragging electrons to it. And the other side of the molecule, the carbon, is partially positive. So that's kind of a weird trick. Different structures, even though these are kind of very similar looking, can be polar or non-polar, and that's going to change a whole lot of their properties. That's it for chapter 5. We have a whole lot going on there. Most important thing is drawing those Lewis structures and then applying the polarity concepts that we learned. The other stuff is a little bit of fluff, but it is occasionally seen on the test, and it's definitely something worth knowing. The intramolecular forces and bond energy is going to be something we talk about a lot in the future. So I really wanted to intro that to you today. All right, that's all I have for you today. Have a great day. See you soon.